if you're tired of diode circuit, you'd be glad we're moving on to a more interesting. I think it's more interesting because that will be our core for follow-up discussion, because the diode circuit will be only a very limited part of applications, but of course it's useful and mostly for power circuits, for charging and for protection. Those are the key application of diode circuits. So the next thing we're going to move on to for operation for amplification. If you actually wanted to have signal amplification, diode circuit will be very hard to be impossible to manipulate the signal to do amplification. So anytime you want to amplify the circuit, if you go back to the history, we talked about the IC history, you should know that the main application at that moment is not actually digital operation. Most of the transistors are built for radio applications. So what they wanted to do is to substitute if you have a radio, if you look at the old-time movies like in the 1940s, the radio is like a big chunk of a thing, consists of vacuum tubes in order to modulate the signal. So if I don't know, I heard that in, I think, the movie King's Speech. He gave a speech during the war, and people are sitting around a large radio that consists of vacuum tubes in order to listen to the voice. So the development of transistor mostly to address the issue of modulating analog circuit and analog signals. So we're going to talk about what are the key component to fulfill that is actually the transistor that we're going to introduce today, which is a BJT, short for BJT. So for chapter 4, what we're going to do is basically going to go through the details of BJT, is short for bipolar. Junction transistor. So the main idea of having a transistor, as I said, if you look at the word itself, transistor is to trans the signal in order to control the resistance. So one of the key components in a transistor is what we call the key component is, we're going to talk about that, it's called the instead of resistance, we typically talk about transconductance. This is one of the key performance factor called GM, which is transconductance. So the idea is that through the third terminal, you want to control the current at the second between the two. So for diode, because it's a two-terminal device, you're unable to provide a structure which transconductance, meaning that you have a third terminal which control the amount of current flow. So it's like if you think about it, a transistor is just, you want to realize a faucet. If you go to the water, in a washer, you can actually want to have a transistor, meaning that I'm turning the knob to control the water. But the stress between the water pressure between the knob does not control the water. The knob controls the water. So you want the third terminal to control the current flow. So how does the third terminal control? How well does one control the faucet will then determine on the transconductance. So we're going to talk about that when we apply that into a small signal analysis. So first of all, before we actually go into the details as to what the importance of having a transistor is, that first of all, let's describe the physical structure of a bipolar junction transistor. So basically, we start with the physical structure, and then we're going to talk about why does this provide a unique IV characteristic allow us to use third terminal. If you think about it, it's actually very interesting because you're not using if it's the diode, your current is controlled by the voltage across this diode. But now I wanted to have a voltage across this point to control the other point. So that's the point of trans. Okay. So the IV characteristic, how does one approach and how does one analyze this IV characteristic? And of course, there's different. We're going to talk about different operation regions. There's actually 4 operation regions. So how does one operate in different operation regions, and then you have different IV characteristics? How does that come about? The background physics as to also the large signal model. Of course, once we have it, have a basic understanding as to how it operates, its operation regions, you want to construct a model which is typically is consists of equations, current equations, and we taught subcircuits. Subcircuits are maybe a voltage source, voltage control current source. That sort of model, you use subcircuits so that we can actually put that into a simulator, allows us to find the operating point, for example. And then, of course, we're going to construct a small signal model that would then contain the most important factors in transistor as to the transconductance. So you actually see something. The key parameter will be GN in this case, the small signal model. Okay? So for physical structure, we're going to talk about cross-section, key device parameters. You're going to generate device parameters. As we said, for a diode, what is the key device parameter is IS. In this case, there's two device parameters, the key device parameter, which is IS. Also IS because this is a diode-based circuit. And then there's beta, called the current gain. So we're going to talk about that in a bit. Okay, so these are the key things you need to make sure that you catch when we move on to more complicated discussion. So we're going to briefly talk about the operation mechanism as well, but okay. So what is a bipolar junction transistor? If I'm going to draw it in terms of there's 2 types of transistor. One is called the NPN transistor. Let me draw it here. And there's the PNP. So there's actually 2 types of transistors that determine on how you stack them. So it's like a sandwich. So NPN simply says that you stack the P with 2 slices of N, right? So your bread is N, and the meat is P. So it will be something like this. So you think about it as a sandwich. So then, of course, so this is an NPN transistor. If I'm plotted in over, there will be 3 terminals in controlling. So each of this area is connected out by a metal. So the blue will represent the metal, which allow us to make a contact into this particular region. So I actually have 3 contacts to the region. There's this collector. Let me highlight it with a different color. Also my color. Okay. So I have 3 key terminals. One is called the collector, base and base and emitter. Let me draw it again. So C stands for, well, let me draw the circuit. So the corresponding circuit symbol, I start with the corresponding circuit symbol. It looks something like this. This is a circuit symbol for bipolar junction transistor. Also 3 terminals, E, B, C. So let me write it down here. C stands for collector. B stands for base. E stands for emitter. Okay? So this is the basic structures of an NPN transistor. Once again, NPN stands for 2 slices of N and 1 slice of P in the center. And the reason, let me explain, come back to this a little bit later. Let me draw the other counterpart for PNP. So PNP will then be the opposite, meaning that you have 2 slices of P bread wrapping around an N region. Of course, you still connect them together out. So the center is still the base. And then I will have the emitter on top, mostly. I will explain why in a bit because of the connection, the current flowing direction. Collector at the bottom. Okay? So the circuit symbol will look something like this. Okay? So that this will be my emitter, base, and collector. That will be the circuit symbol for a PNP transistor. This is for PNP. The left is for NPN. Okay? So let me stress one key important thing. If you look at the symbol, it's not a symmetric, even though if you look at this, if you look at the illustration, it looks like if you look at the sandwiches, it's supposed to be symmetric, right? If I give you the structure, it looks symmetric. But in real case, if you flap it open, there may be mayonnaise on one side. There might be not. So it's not an actual symmetric structure if you actually look at the real cross-section of the device. And also, emitter and collectors are made differently. Therefore, it's not a symmetric device. You have to recognize that. For MOSFET, it's actually a symmetric device. This is an asymmetric device. So first of all, it's an asymmetric. Even though it looks the same because collectors and emitters are typically made differently, are different. Even though they are the same type, for example, the doping concentration is drastically different. Okay? Secondly, the error in emitter size. So remember, if you look at the symbol, the error is always at the emitter side. Whether it's going out or going in, and it indicates, the second thing is that it indicates the direction of current flow. So if you think about it, this is my PN junction. So my PN junction, if a 4-bias PN junction current is flowing in this direction, it's always flowing in this direction. This is the PN junction. The 4-bias PN junction will allow current to flow in this direction. So the arrow will always be on the emitter side, and the direction of the arrow will indicate current direction. Okay? Last thing, I want to talk a little bit on the naming of the terminals. So you get a sense as to why they name it as it is. The main reason for these type of naming is because, as I said, when transistor was developed, the main goal is to substitute what? Remember? Vacuum tube, correct. So in vacuum tube, there's emitter, there's collector. Remember, I have the emitter electron beams, and then there's a collector on the other side. So you see these names, you know that it's actually closer to the vacuum tube area because they use this type of name in order to describe similar behavior as to that in reflect in vacuum tube. So what does it mean in collector? In this case, on base is so basically you have two terminals. Collector and emitters are if you look at the name, you'll see that it's actually the two terminal which will actually have the current flowing with the current that you want to control. And base will be actually the control node. Typically, this is the control terminal. And to control the current flowing between these two, the collector and emitter. So why is a flip in collector and emitter? Anyone think about it? Why? In PNP and NPN, why is it typically the emitter in NPN transistor is at the bottom, and the emitter in PNP transistor is typically at the highest voltage terminal? Why is it a flip? Can anyone think about it? So what are the main character? Of course, a bipolar junction transistor is actually a more complicated device, if you ask me, because it has two types of current. It has electron currents and hole current. But for NPN transistor, you want to control mostly electron current. So this is for the control of electron, even though they have hole current, but the main component is electron current. For PNP transistor, of course, it's the opposite. So it wants to mainly control, the main current is to control hole current. It's I should say, hole current control device. So mainly you want to control hole current. In this case, the main control is electron current in this case. Okay, so if the main carrier you want to control is electron, meaning that in this case, my electrons are moving electron. You think electron should be blue or red? I'm always confuse myself. So let's say electrons is red. So if I have electrons emit from emitter goes to collector. Okay, so that's the main operation of this device, is to, through the base voltage, to control whether there's electrons going from emitter to collector. So your main carriers are always going from emitter to collector. Okay? In the opposite side, I would then mainly have holes through the control base from emitter to collector. So based on this, another key summary is that the main carrier, I want to emphasize it. Of course, there's minor carrier. So the main carrier is always, on operation, always moves from emitter to collector. So you emit the carrier. The basic idea of using this name is that you always emit the carrier and then allow the electrons to move from emitter to collector. But the current flow in this case would then be the opposite. So your current will go from here. Your collector current is expected to go to the opposite. That is why we're having emitter at the bottom, because you emit electron from the emitter to collector, emit holes from emitter to collector. And the current direction is the same. For in this case, your current direction, let's say IE, is the same as hole current. I'm using IE. We're going to talk about that in more detail. So the main current through the base, I should say through the base, will then be construct mainly. Let me not I'm afraid that I'm going to make some mistake. Let me just draw it down here. Because we typically only look at collector current. So the collector current will mainly be the whole current coming down from emitter, and you collect it. Okay, so the current direction for MPN is opposite. The main current, electron current is opposite direction as the current direction. Therefore, you flip the direction. Okay? Okay, so these are the things I want to mention as when we introduce this. So the second important thing is that because we have two junctions, if you look at this, let me redraw this again. So we're going to focus ourselves on NPN transistor first. So once again, you have connection of collector base and emitter. Okay? So how does one, if you want to realize this, typically what we actually want is to have a lighter dope collector. So there will be doping levels. If you think about doping, we're going to talk about why, but later, but just to give you a sense as what we actually, toward more optimized performance of a bipolar junction transistor, you want, this will be your doping concentration at each region. Or if I want to be more specific, this will be donor type. Let me use a different color. MB. This will be a acceptor. These two are donors. So if I use the, okay? So how does one, if you want to make a bipolar junction transistor, you need to use the idea that we introduced to you, which is the counter dope idea. So you need 3 layers of structure. So typically what we have is that you typically start with a P substrate. And then you define a certain window for your collector region. So this is the cross section. So you actually see 2 views if you want to see a device. This is the cross section, meaning that if you cut it, the cross-sectional view. You cut along the transistor. So there's, and then there's the top view. So you start with the wafer, and then you define, this is the collector. So if I'm cutting it over along this line, so this is my AA cross section. This is AA cross section. So I need to define a collector region. Let me use a different color. Collector. So you start with a substrate and you define your collector with a green mask. So meaning that I'm opening this window and I'm going to dope it with NC, right? So if I'm cutting through the cake, what happens is that you will see a deep region look something like this. So this will be doped with NC. This will be then N-type. A lightly doped, typically a lightly doped region. So I could label it as N minus. Okay? And then I'm going to surround this with another mask, another window with the base. I'm open it up and define this region as base B with a NB. This will make it a P-type, so I want to make it dope a little higher. So then it will counter dope So then it will be a smaller well inside within. This will be MB. This will then turn into a p-type region. Okay? And finally, I'm going to dope my emitter. So I'm going to make a mask, corresponding mask right here, a smaller mask. Okay? So this will then be doped with a Ne. So this will be Ne. And I'm going to dope with a typically more heavily doped donor. So it will be M plus. So then finally you're going to make contacts. So you're going to have contacts. So if I'm making contacts, there will be contacts right here. I'm just assuming that you're making contacts. So just ignore me. So this is just to ensure that you have a good contact. So on the surface, you want to make sure that you have contacts. So this will be your emitter contact. This will be your base contact. This will be your collector contact. This is how you make the device, a NPN. Okay? So in this case, I would then make a contact. This stands for a contact. So if you ever learn how to read a layout, that symbol represents a contact, meaning that I'm going to land a contact here and a contact here. And typically, when you land a contact, it will do this automatically. Okay? So what is the key parameter in a bipolar junction transistor in terms of device structure? How does it link? Aside from these are technology parameters. How do you determine NC, MB, NE, are engineered at the foundry side? But as a designer, what is the key? You simply draw the layout. So the layout, you can draw the ones that determine the characteristic of a bipolar junction transistor is actually this. What color is it? If you look at a device, this is the active, typical active region. It's a vertical device. My electrons goes from emitter to collector through the stem base. So if you think about it, your electron, my electrons are, so electrons moving from here to here. So actively, operation region is actually through this area. So only this region, these are all for connection. So if you look at this, what is the key important factor is this. This is called emitter area. So actually, the cross-sectional let me finish the sentence and come back. What does this mean? It means that if you think about your device as a tube, the cross-sectional, the size of your tube will be determined by emitter area, because this is the active region which allows current to flow from here to here. The red, the blue doesn't actually count anything. It will just give you the contacting area or the surrounding area to make sure that your isolations are good. So these are mainly for isolation and contacts. This is actually the active area which would define the size of your device. The rest is just parasitic or peripheral to service the device. Okay? So once we know how to make the device, the next important thing is to understand that the device consists of two junctions, right? I have typically, if I look at, let me draw this again. NPN. So if I look at this, this is if I look at this, there will be two junctions. That is why it's called bipolar junction transistor, because it has two polarities, and it has mainly saying that it has two junctions. So I have two junctions. One is, this is or sometimes referred to as the collector. Let me highlight it again. Base emitter. So if you look at this device in symbol, this will be VBE. I'm using B as the beginning because I want to make 4 bias as positive. Defining, once again, base emitter collector. Okay? So this device basically consists of two junctions. So the junction has two modes, forward and reverse. Therefore, there's how many modes? It's a math problem. How many? So each of this junction can be forward or reverse. So the combination of these two are 4. Yes. So if you look at typically, let's keep it. So this is, let me write it down here. So J1 is referred to as the BC junction. And where J2 is the BE junction. So as I said, because there's two junctions, they can either forward or reverse. Therefore, you can assume that this device would then have 4 operating regions. So to discuss this, we typically use this plot as to look at how much VBE and VBC. And this is a little tricky because we know that for the diode to turn on, it will then need a on voltage. So we'll then typically use a line. So this is VBE on. This is the same as a diode turn on voltage. It's the same as VD on. It's just a limit specific for BE junction. So it's the same as the turn on voltage for diode. So when it's on, so this is the reason why we're only drawing this line on the BE rather than the, we're not really care of the BC junction is that when you turn on the device, BE junction is the main control. So you want to make sure that it actually turns on. And the voltage on the collector, or the voltage difference between base and collector, is mainly to provide a suction force of your carrier. So we're going to talk about that a little bit. So the reason why I'm drawing this line typically on VBE on is because those are the main turn-on component, the parts that control the turn-on current. So there's 3 regions. If both of them, so if in this quadrant, means that both junctions, if I'm just going to hand wave, and this will be J1, J2, are both considered forward. So what happened is that if you, this region is referred to as saturation. I will explain a little bit on why, but the way to think about, let me describe it later. So then you have both junction forward, meaning that the way to think about it, or a good analogy, is that you have refugee coming from the front, you have refugee coming from the back. So 4 bias, remember 4 bias, you have minority carrier injection. So then, which means that the country will be full of refugees. So that's why it's called saturation. So the saturation simply means that it's saturated of minority carrier. So you have refugee coming from the front and back, and then you saturate with minority. And then the second region, which is second. which is the second. I should say this one. It's not the second quadrant. This is actually the fourth. But the second region we typically refer to as, this is called active. This is where you actually want your transistor to be. So active is the most favored operation mode for having a transistor as an amplifier. So, which is J1 reverse and J2 forward. You have one forward junction, one reverse junction, and also you want the forward one to be the BE junction. So typically you want BE junction forward, BE forward, BC reverse. Okay. So this is more like, as I said, saturation is both junction forward bias, minority carrier coming from both sides. Then your base will be flooded with minority carrier. Therefore, you're not actually promoting current flow. In this case, I'm forward biasing a junction reverse biasing, meaning that I'm favoring directions as to where to go. So it would then favor the conduction of current. So this would then maximize IC. This is actually the one that we want to control. Okay, so then allow a direction of current flow, favor current coming from one direction, moving to the other. We're going to talk about the detail later, but just to give you a qualitative sense as to what happened. And the third part is actually very easy. Third part is off. Call it cutoff. Because both junctions are reverse. In reverse, therefore, you only need to deal with leakage current. You don't actually consider that. It's all off. Both of them are off. And lastly, this is a slightly tricky part, is that you can turn on, there's another combination, the fourth part. The fourth region, which is the second quadrant. I should follow. Should I do that? Okay, let me just make sure that I follow the law of quadrant. So this is the fourth quadrant. This will be the second. So in the second quadrant, you would then have J1 forward, and then J2 reverse. This is referred to as reverse active. It doesn't mean that it won't allow you to have a current, but it's not. It's like when you make a device and you're not working, you're not operating in the right direction. You're sort of like upside down. You're making it upside down so that it's a poor performance. It still works, but it's poor performance. We're going to talk about why later. So you typically don't want it to operate in reverse active unless you make a mistake. So this will only happen when you make a mistake. So for transistors, let me say it again. If you wanted to use a BJT for amplification, for signal amplification, to provide amplifier for signal amplification, you want your device to operate in active mode. This doesn't exist unless you make the mistake. And this is if you want to make it into a digital circuit. Even though we know that bipolar is not a digital operation typically, but if you want to make it as a switch, then it would jump around between the two. So what color? I have the green. Or digital. If you're doing digital application, meaning that there's on and off only. So this is the off, this is the on. You're typically jumping between the two if you're doing inverter type of application. Okay? Good? Clear? I don't think I have time to go into details on how they operate. So I'm going to outline what we're going to talk about on Thursday. Once again, we're going to have our quiz, the second quiz on Thursday. Remember to see to update your schedule. We have the updated version on EE class. Don't use the last one, the old one. If you see the quizzes on Tuesday, that means that it hasn't been updated. Our quizzes for the following semester will always be on Thursdays. Okay? So make sure. So let me wrap it up with some outline as to what we're going to tackle on Thursday. So we're going to talk about currents. So as I said, if you go back to this discussion, you have electron currents. So why we're going to talk about, of course, there's different operating region. We're going to talk about, of course, the active region where you forward bias one junction and you reverse bias another junction. So the basic idea is that when you forward bias PN junction, remember what happened is that your minority carrier diffuse, right? You have minority carrier diffusion will then go through the other side. So these minority carrier diffusion, if I have a reverse bias junction close by, the reverse bias junction is like a vacuum. So what happened is that this is very similar to, so I'm just going to give you an analogy as to how bipolar junction transistor work. Is that I'm standing in the front in a BE junction. So when I forward bias BN junction, meaning that I'm spreading I'm holding a perfume. So I'm spreading the perfume. So if I'm spreading the perfume, you will actually see the perfume particle diffuse from the front because there's a lot of them and diffuse all the way to the back. So if I don't do anything at the back, what happens is that there will be a stabilized output level. But if I put on a vacuum tube or a vacuum system at the back, what happens is that whatever is coming in will be sucked out. So any minority carrier coming in will be sucked out by the minority carrier force. So then I would then maintain a good current float from emitter where I putting on the perfume, and the vacuum will then suck up all the perfume. But because the current come in two types, there's electrons and holes. I'm only taking electrons. My suction system or my vacuum is selective. It only selects electrons. Even though if I'm forward bias PN junction, there's electron current and hole current. Remember, the diode current is electron current and hole current. So if you think about bipolar junction transistor, the analogy I use in most cases is like a current splitter. What it does is that it splits electron currents and hole current. So it only takes in the vacuum only takes in electron current. So the hole current will then be provided by the base, and the electron current will then emit. The emitter will provide electron hole. So there will be electron current. I'm using the wrong color. Let me just make sure I'm consistent. So this is my electron current, and this will also provide hole current. But the hole current will go here, and the electron current will go to collector. That's what a bipolar junction transistor, when it operates in forward bias in active mode, is actually doing is splitting the two types of carriers, two types of currents, so that I would then have electron. This is selectively only sucking electrons. Rather, it will push away holes and then will go to base. So you separate these two, allow you to have a better control of your main current is actually this electron current. So how does we maintain that will be the topic of our next lecture. That will be very interesting. So make sure you come. I think it's very interesting. Let's start today's discussion. We're going to have an hour and a half lecture today, and then we'll have our second quiz. So get ready, make sure that you're ready for second quiz. So what we want to do today is continue our discussion on bipolar junction transistor and as to what we're trying to achieve. I want to spend a little time outlining as to what do you expect for a transistor. As I said, for transistor, there are basically two functions. One is, for digital circuit, it's the switch. So you think about whether it's on or off. So whether you want to turn on or turn off. So you basically operating in two modes, as I said. You basically, whether you turn it off or you turn it on and in a saturated mode. But the basic idea of a switch is whether it's off to block the current or block the voltage, or it's on to allow the current to flow. But for amplification purposes, as this class will focus on more, is that you want to have a transistor allow you to process the signal. So the basic idea is that you wanted to have something more like this. You want to achieve, remember for an amplifier, let's think about an amplifier. You want to have like small signal. If I'm talking, I want my signal to be amplified. So in amplification type of operation, what you basically want is to have a device which to pick up the small signal and modulate it in terms of taking in the input signal and modulate it into an output, whether it's a current or it's a voltage. So if you look at that as a voltage, a current modulation, meaning that if you twist your faucet like a little bit and then the water changes a lot, that means that it will then provide large enough gain for your subsequent signals. So the basic idea is that if you're doing amplification type of application, mostly analog or for realizing amplification, you then want something more like this. So if for an ideal transistor which modulates signal, you want to take in a voltage. So this will be my input side. So in the circuit point of view, you want this to be your input terminal, and this more like your output terminal. So a transistor would then deliver something like, if you take in a voltage, and because the input voltage is applied across a terminal, this voltage can modulate a current. We call the output current. We wanted to have a voltage control current source. Basically, you want to deliver, in terms of circuit theory courses, you want to realize for example, if you're having a circuit design, you want a voltage control current source. How does one deliver this? How do you actually make it? Transistor is a way of realizing a voltage control current source. Okay, so that's the basic idea. You want the third terminal to control the input voltage to control the output current. That's the basic idea. So this is what we wanted to achieve if we're making analog circuits or doing amplification. So then this is what the analogy to a bipolar junction transistor is. So you wanted to have the control, which is at base terminal. If you look at this. So this is B. Let me highlight it. I have 3 terminals. Once again, I have emitter, base, and collector. So typically, if this device is used as amplification, what you wanted to achieve is that the modulated voltage across base and emitter. Emitters typically refer as the ground. So your signal is coming in across VBE. Through this modulation, you want to modulate the collector current. So what we want to deliver, or our subsequent analysis will allow us to establish this relationship. So you want to see what happens and what is the physics and derivation of IC as a function of VBE, and what is the key parameter in delivering the responses of current in response to your input voltage, which is VBE. Okay, so this is what we're going to do today. So we're going to go back to the structure a little bit. So remember, we already talked about some of the students ask me that when I talk about device structures, I'm putting emitter on top. The reason for that is because for NPN transistor, I'm putting emitter on top. This is because how you build it, your emitter will be the top of the surface, close to the surface. But if you look at a transistor in circuit point of view, the emitter is typically at the bottom. So you can flip it in any direction in order to deliver what you want to discuss what we want to talk about. So now I'm going to flip the NPN structure downwards, meaning that I'm using the flat structure. So you can you can flip it around with whatever purpose you want to compare to. If you're comparing to the circuit symbol, then emitter will be at the bottom. If you compare it to structure, emitter will be on the top. If you want to talk about current direction or want to talk about a carrier distribution, I was just going to put it in a flat direction. So this will be my N, P, N. Let me draw that. So we're going to talk about, oh, I forgot to discuss one thing before we actually move on. So remember, there's two junctions, as we said. So this is N, P, N. If we're following collector base emitter structure, there will be junction 1, junction 2, right? So we already outlined that if junction 1, this is forward, this is reverse. So this is reverse, forward. So we already outlined that if both of them forward, it's not actually the mode we want to talk about. This is saturation. This is active. This is off. Both cut off. And this is reverse act. So you already know that there's 4 different modes depending on the forward and reverse bias of the junctions. So we're going to limit our discussion for now on this most important mode, which is the active mode, because we want to talk about the real analog operation. That's the key of the transistor characteristic, okay? So we're going to start by outlining what happens if I have two junctions. Remember, let's say this is my emitter. Okay. Let me outline it on top. Emitter on the left, there's the base, and there's collector on the right, okay? So if this is my physical structure, I'm outlining it in the flat direction. What happened is that I have junction 1. According to that plot, this is junction 1. This is junction 2. Okay? So junction 1 is in reverse. So what happened is that if a junction is in reverse, you will expect that you will have a natural depletion and additional depletion. So that on this side, it will look something more like this. Give me a second. I want to use I'm probably going to use all the colors. So I have depletion charge on this side. So you think about it, I would then have positive charge. This is, remember this is Na. This is Nd in collector. This is in base. This, I should do it in a different way. So this is Nd in collector. This is Nb, I should say. I'm using C, right? And Ne. And remember, these are donors. So these are donors. Donor type, donor type. And this is acceptor. Different type. Okay, so when electron depletion, remember depletion, when acceptor accepts the electron, it will then carry a negative charge. So there will be depletion in this side, and there will be positive charge on the other side. So we then create a, this will be our, use the yellow. So this will be the depletion region. And it actually widened because I'm reversing biasing junction 1. So this is in reverse. J1 is in reverse, remember? Okay? And on the other side, the J2 is in forward. So in forward, what happened is that My structure is too narrow. Give me a second. Let me try to move it toward the left. So I'm expanding my base a little bit so that I could illustrate it better. So if this is my N, I'm extending my base. Okay? So if I'm forward biasing this side, what happens is that you will expect that there's a small little narrow depletion region, but I'm forward biasing, so therefore the electron, I start with, so what happened? So I'm going to give the background. So this is the background, which is NP0. So NP0, remember NP0, this is the inside base, which will be Ni squared divided by NB. Right? My base doping will determine my background minority carrier concentration. So this is not talking about adding bias, but if you're adding bias, what happens is that this is the use a different color. So this is the background condition, which is the NP0. Now, if I'm reverse bias on this side, what would happen? Does anyone know what happened? Law of junction tells us that it will actually drop. So on this side, it will actually drop close to 0. So at this node, you're assuming that at this particular node, it will actually close to 0. It will be NP. If I'm writing down the equation, it's actually be the reverse, whatever diode voltage exponential Vt, right? So if this is negative, because J1, this is negative, therefore, at this particular position, let's assume that this is x. This is x equals to 0. This is x. We're assuming that this is close to x equals to WB. We're ignoring the depletion effect, just assuming that this is close to x, which is WB is the distance between the two. So let's say this is WB. It's the base width. So there, let me summarize this. So we start with doping concentration Ne. These are device structures, device parameters. So Ne, Nb, Nc, these are device structures. And of course, how wide the base is also device structures. So we have base width defined, we have doping level defined, and we can start discuss the characteristic of the bipolar junction transistors, okay? So these are key parameters, let me highlight. Doping concentration of the 3 region and the distance between the 2 junctions. These are the key in engineering or discussing or analyze a bipolar junction device, okay? So as I said, at this particular, I'm trying to highlight that this is V MP at x equals to WB. So if you want to find out at the right-hand side what is the doping concentration, it's actually close to 0 because this is, if I'm drawing this, this is actually VBC. Right, this is junction 2, so it's a voltage across is VBC. And we know that VBC is smaller than 0, therefore, even though you start with a fairly low minority carrier concentration, is getting even lower because law of junction pull it down. So on the left-hand side, what happened is that you will raise the carrier concentration, right? Because I'm forward biasing. So I'm assuming that at this point, this is NP at x close to 0. Let me say, and at this point, we're using NP at x close to WB. Okay. Anytime you want to define your diffusion current, remember we have electrons here, a lot of electrons here, a lot of electrons here. So you need to bridge the gap. So how does one bridge the gap? You create a diffusion current. So diffusion current is defined by what? Gradients. So gradients is defined by distance, and you pinpoint the boundaries. So once we have these boundary levels of carriers, we can then find out the slope. So once we know these two, I'm assuming it goes like that, and then I can get the slope. So this will give me dn dx. And then the electron will then flow from here. We're going to get the numbers, but the basic idea is that you pull down the minority carrier concentration at the collector end, and you pull up the electron carrier concentration on the emitter end. So then we create a slope so that the electron will actually come in. So this is the electron diffusion current. You create a large profile, and then this current will come in. This electron current will come in from the emitter and then all the way through here and go out at collector, becoming collector current. And the reason why this happened is that if you think about it, my junction 1 is reverse bias. So when we talk about a diode under reverse bias, we're assuming that the current is 0. The reason for that is because depletion approximation tells us that there's no carrier. But in this case, there's carrier. The carrier is coming sipping from the border. So if you think about it, if I have electron diffused at this edge, it will be sucked by this electric field. I have a large electric field going this direction, pushing electron through the gauntlet. Remember, there's a large diffusion. So diffusion, the reason why typical reverse bias PN junction does not carry current is because there's no carrier. But I'm feeding carrier through this diffusion. I'm feeding it through so that once it goes into the depletion region, it will be pull over. So one electron comes, it will just go over. So you have large electric field to pull it. So the analogy will be, I have, if this across the room is my base, I have a vacuum or a fan at the back. So as I said, if I'm pumping perfume at the front, so then the back vacuum will then suck up whatever diffused through the space, and then it will suck up the perfume particles, right? So if I'm not pumping, if I stop pumping, meaning that if I turn this junction off, what happens is that there's no feeding of carriers, there's no feeding of electrons. Once there's no feeding of electrons, then there's no perfume. You will not see perfume even with the pump, even with the vacuum pump. Okay, you see the point? So it doesn't, the reason why we're setting up this is to, so the idea is that I forward bias PN junction to set this up high and have depletion to suck up whatever is coming so that I could create a good profile allowing current to diffuse through this region. So this is the basic idea, okay? So let's think about how does one determine the collector current. So as I said, the purpose is to find out what is the level of collector current. The reason why we're concerned about collector current, of course, is because that's the current that you want to deliver to the output. So what is the key important collector current? So first of all, if you look at this, collector current consists of okay? This is very important. It's not a diode current. If you think about a diode current, you have collector current, the whole current. You sum it up, and that will be your total current. But for collector current, it's only for, well, this is for NPN transistor. I want to highlight, if you're doing PNP, then it will be the reverse. So for NPN transistors, your collector current is electron current. The reason why isn't whole current going into your collector? There will be hole coming in from here. I will have holes. Because this is a 4 bias PN junction, so there will be rising of holes, right? So this will be the hole current will come in from this direction. So hole will come in from the contact, from the base, and then it will flow to the left. Does anyone know why isn't hole flowing to the collector? Why isn't? Why isn't there any holes going into collector? Yes, because of the electric field. See, if a straight hole, if the hole straight out goes to this direction, the electric field will pull it back. So it will not favor hole flowing. There's no hole will flow. There's no hope for this hole. It will be pulled back by the electric field so that the hole will only go into one direction, which is to the emitter. So this is the hole current. So what happened is that if you look at the whole picture, what happened is that my collector current, let's say, so if you think about the junction, the p-n junction, I have electron current that will go to collector. I have hole current that will actually come from base, only for the base to supply. And the electrons and hole current has to be supplied by the emitter. So this is the p-n junction that we have, the typical p-n junction. A p-n diode. If you calculate the current of a p-n diode, it will simply be, remember, if we go to a 4-bias p-n junction, what we do is that we add up the electron current and hole current. That will be my total current. The total current will be supplied by the emitter. And some of them are coming to the base, or going to the base, if you think about it. Some of them going to the base, or some of them going to the collector. They separate by type. So if you think about, another way to think about this is that the total amount of current for a 4-bias p-n junction consists of electrons and hole current. The electron current being selected by this vacuum, by this depletion region, only the electrons go there, and the holes are coming in from the base. So it's like as I said, this device is like a current splitter. It will supply, it will selectively only pick the type of carrier that I want. I want to pick the electrons, or I want to pick the hole, depends on your structures. Okay? This good? So after this qualitative discussion, I want to go into more analytical analysis as to, remember, the purpose is to establish this. I want to know how does the input voltage, which is V, how does the base voltage control my collector current? That's the whole purpose of having the transistor. So what determines collector current? In this case, what determines collector current? What type of current it is? What limits your collector current? Drift or diffusion? Which? Pick one. Drift or diffusion? What? Diffusion, of course. The reason why I want to emphasize this once again, I probably need to talk about this a few times because I don't actually get the concept myself when I'm taking the class when I'm your age. So the concept is anytime we discuss of a current flow, you have to think about it. It's flow. As I said, if you put yourself in the role of an electron, it will diffuse and drift and diffuse and drift. So it will go through all many type of transport to go through a loop of circuit. So anytime we said that I'm talking about drift current or diffusion current, is basically we look at the propagation of this carrier through the loop at which side, which will be limiting the current flow. So you only look at the limiting part, which part is the most limiting part. So in the travel of electrons to collector, it will of course take diffusion and drift, right? So if I'm looking at an electron through this process from point 0 to WB, it will be diffusion. And from here to here, it will be drift. And follow to the neutral region is actually mostly drift. if you actually want to think about what happens. But what we talk about is that this is not a limiting factor because the vacuum tube, or I should say a vacuum pump, will take whatever comes in. So you just feed it in and it does not limit your current. The part that limit or control the total loop of electron current through collector will be limited by diffusion current. So we're going to talk about how does this diffusion current being controlled by your 4-bias PN junction.